Okay, so we're gonna, first of all, I just want to remind you, so we don't actually have to really focus on R this week or RStudio. You'll see that I have the screen open to RStudio. I encourage basic math problems to try to utilize R within that context, and actually I even have a folder with essentially every single problem set that we've ever done before. That being said, we need to take the big picture and we need to focus on the core concepts and the core elements. So I have two approaches toward this. One is I could be more directive, and I could tell you what I think are the main concepts where I see students maybe sort of stumbling a little bit more or just having more questions, or feel free to chime in and ask me about particular questions. What I'm not going to do in particular is I'm not going to actually really focus on the practice exam. I encourage you to take the practice exam. You'll see the answers there, but I don't think it's any value added if I just walk us through the questions. If you have particular questions about the practice exam, feel free to go ahead and ask. Otherwise, I'm going to focus mostly on, I'd say, the last few weeks, which are, in essence, are simple linear regression, and you'll get the answers for that soon, hopefully tonight. And then I'll focus on correlation and covariance, and then on this stuff on probability. You'll see actually some script on probability. That being said, I want to know if you have any questions going forward, because this is your opportunity to actually ask questions related to the midterm exam.
I have a question on the Whisker box or Whisker plot.
Yes, the box and Whisker plot.
Yes, so I tried to find this in the book and even on the lecture, but I couldn't figure out the dot that they put in the middle, if it was the mean or the median. And I know the book said the median is the half of 50%, the 50% mark, and yet the two different Whisker plots, well, I couldn't determine for sure what that dot was.
So are you talking about, this is you, Caroline, is that right?
Yes, yeah.
Caroline, are you asking about in particular the problem set where we have the dot?
No, I've just seen the dot in different places, and so that makes me think it's maybe the mean instead of the median.
Okay.
Because originally, I think the one in the lecture, it's right in the middle. I'd have to go back to look, but
yeah.
So then I thought that was the median, but then it's not always in the middle.
Yeah, so that's a relevant question. Let me see if I can get us to the script for that, just so I can illustrate for us what, just for the rest of you who may have questions, what we're talking about here. So here, this is in problem set number 2 I just have loaded. I have all the problem sets, by the way, in one working directory. So I'm gonna see if we should be able to run the script here. I'm just gonna load the within RStudio the script. Well, why aren't we running this? So I'll show you how to interpret the box plot. Long story short, the middle of the box plot is actually the 50th percentile. Is that a surprise to you, Caroline?
No, I did understand that, so that's the median.
Right, exactly. It is. What's another term for that, by the way?
Q2?
Exactly. It's the second quartile. So I kind of think of the box plot as that median, rather, as something where if you just split the sample in half, and we have a couple of questions related to that, so that's in the practice exam. So that's sort of a cue toward maybe identifying or recognizing that as an important question for the actual exam. So let's see if it wanted me to restart. So I just would love for us to see that work example of the box and Whiskers plot. Let's see if I can get that up and running. Oh, you know what? I actually don't have the data set in here, I believe. So that's fine. This is what I'll do. Let's see. why don't I direct you to the lecture notes, and I'll take you to the slides where Ethan actually talks about the box and whisker plots, and we'll sort of focus on that. Is that what you'd like, or do you just want that specific answer, Caroline?
Yeah, no, that's fine. No, I was looking for the general because I was getting confused of what all the little things were.
Okay. Well, it's interesting to think about the box and whiskers plot, or box plot as it's commonly known. So think of this 50th percentile as the second quartile. You'll see this in the practice problem set. So here you have the first quartile, right? Imagine you take any numerical variable, not a categorical variable, and you split it into 4 quarters. Here you have at the 25th percentile, 25% of the people or cases or observations lie below that quartile. That's the Q1. Here you have Q2, which is also known as the median, or the 50th percentile. So there are 3 ways of describing that. And that's that middle line of that box plot, I think, or dot. But it should also be the line in the middle of the box plot. And then you have the 75th percentile. And you'll see that the box plot will describe these 3 parameters in the sample. It will also, that's also related to the IQR. What's the IQR? If anyone would like to chime in. Well, the IQR is the measure of spread, right? It's the interquartile range. So it's the 75th quartile minus the 25th.
Right. Q3 minus Q1.
Exactly. So, and this is the 3rd quartile, and this is the 4th quartile is the maximum. So if we go to the box plot, let's see where we can find that. I'll just do a Control F box plot. Hold on for a second. Oops. Shoot. Hold on for a second. I accidentally into full screen mode.
There's one on page 93.
Okay, thank you. For some reason, let me stop my share because for some reason I accidentally have a problem with my slides. Okay. Okay. So you're saying page 93 of week 3, is that right? Let's go to that.
I think I got it out of week 5, but I could be wrong on that.
Okay.
Maybe that's why I couldn't get the definitions of what each thing meant, because I got it from a later week.
Okay. Oh, here it is. You'll see it on actually page 176 of week 3. So let me share my slide. Let me share my screen. I'm going to share week 3. So here you should see the box plot right here. And this is an important device because it is actually commonly misinterpreted. Oh shoot, I guess I can't zoom in now. View, fit width, there we go. So these are the elements of the box plot, also known as a box and whiskers plot. Now, if you notice, Caroline, you're correct, that dot is the median. And if we look at the popular kids data set, I believe the median for age was also the quartile 3. So sometimes you'll see that dot perhaps pushed over to the right and it'll have the same value as the 3rd quartile. But the main point is that this is considered a kind of robust statistic, a statistic that is robust to outliers. In fact, it's used often to identify outliers. So what I want to identify here for you are these elements, which are the 1st quartile, the 2nd quartile, and the 3rd quartile. Sometimes this is actually drawn as a line. I forgot that we actually use this as a dot here in this graphics package. It's commonly portrayed as a line bifurcating that box. But the main point is that Q3 that value minus Q1 equals interquartile range, which is considered as a measure of spread. The median, or the second quartile, is considered this measure of central tendency for a numerical variable. And that these whiskers here identify those observations that are considered outliers, and you will actually be able to see those outliers here. So, and it'll also identify skew. Now this is an issue that we have when we look at numerical data. I'm going to address this because I saw this issue when grading exams or problem sets. A lot of people had flipped the definition of what a skew is. We can see that these data are skewed. Is this right skewed or left skewed? Would anyone like to chime in?
Left skewed. Left skewed.
Yes, and who was that? Who said that?
Caroline.
Caroline, yes, exactly. And a lot of people would say this is right skewed rather than left skewed. Caroline, how would you identify this as left skewed?
Oh, because the outlier is over to the left, so it pulls the data that way.
Exactly. So think of that as I love your terminology, and that's exactly what Ethan had described in lecture, and what we're trying to emphasize is that pulling of the data, numerical data, by these outliers. So Caroline, not to put you on the spot, but let's continue this line of thinking. What do we see if we have an average in a left skewed data set? What do we expect the average or mean to be relative to the median? If the data are really left skewed, where does the mean lie relative to the median?
I think to the left.
Lower than.
Lower, exactly.
Lower than.
Now, in a symmetric distribution, what happens to the median versus the mean?
It should be the same.
It's on center.
Exactly. So you could have actually say, if we took this data set right here, and I had, let's see if I can draw here. Let's say I'd identified some outliers here. Oh, look, that's kind of fun. Thought I could draw. Yeah, okay. So if I had some outliers here, and I had two outliers, we'll put three here, but 1, 2 here, we would still expect this, we'd even expect this whisker to be spread out a little bit more. If this distribution were more symmetric, then we'd expect the median to equal the mean.
Right. I still am wondering, though, why the median isn't right in the center of the box, like visually. Is that not?
Oh, that's a great question. Was that you, Caroline?
Yes, that's Caroline.
Yeah, thank you, Caroline. That's a great question. So the median itself is an actual value in the data set. So the point is not whether or not it lies, the numerical value actually lies there. It tells us more about where it lies with respect to the others in the sample.
Sets. Right.
So let's assume that everyone in the class gets on. See if I can do the whiteboard. I'm going to share this little. I'm going to clear all drawings, and I'm going to do a new share. And I'll share a whiteboard. And I'll try to do the best I can in terms of drawing. I failed handwriting in 5th grade. This is just my life. In general, so here we have the median, right? Geez, that's a lot harder than I thought. Okay, here's the third quartile, Q3, and then here's Q2. Now, the point is, what we're describing is how you lie. Imagine yourself within this distribution. Where do you lie with respect to others in the distribution? So you can take on a numerical value that makes the box plot look kind of squished over to the right. Say, for example, the range of exams were, let's erase this right here. Let's just assume, we'll do a new draw. Let's assume that the exams were scaled. Everyone did really well in the exam. And here we have 100. And then here we have 80. And 50% of our sample, this is where that dot would be if you use that same graphics package, got a 95. What this tells us is that half of the class got this range, and then half of the class got below this range. and that we could even say maybe if we had a minimum, maybe nobody got below 80. But the point here is that this is 50% of the distribution. That's why it looks a little skewed, even though it's the 50th percentile. Does that sort of clarify your question regarding that issue?
Yeah, I think it does. But so then the Q1 right there, that would be at, let's see, what would the number be for Q1 on your little chart?
Well, that's a great question. The Q1 actually isn't illustrated by the box plot. Q1 is the first quartile, and that's in Q3 is actually the fourth quartile, which means that what is the definition of Q3? Well, it's also the maximum. Q1 is also the minimum, because if you are at Q4, then you are at the 100% of the sample lies below you, right? So that's actually the range. You can think of Q4 and Q1 as actually the endpoints of the sample. So these whiskers are actually the halfway points between Q2 and Q1. This is the halfway point between Q3 and Q4. So we often that's how we often identify outliers, is 1.5 times the third quartile, or splitting the difference between that in that upper quartile, the top 25%, we split that in half. Then we have what remains is 12.5% up here, or the bottom 12.5%. That's commonly misunderstood, I have to say. But the main point, and I'm going to take us back to the slide, because I think this is relevant. If we look at the slide here, this is where it's useful to actually see. This is where the box plot is actually quite useful, because not only do we see the distribution, we also get an idea of its actual value. We could guess this value to be about, what, 72, 73. So even though it looks kind of squished, maybe this distance is shorter than this one, right? We actually are positioning our data to actual numerical data or values. It's really an effective way to actually see our data. So the reason why this might look a little skewed or might look a little off is precisely because not only does it describe our sample distribution, it also gives us the benchmark of our value here. So these are great questions. I love this. This is very important for, I think, understanding numerical and categorical data. We have quite a few questions about those.
Nate, Payal, can I ask you a question?
Yes,
here?
please. Payal?
Now that I'm thinking about this more, this is great. How do we treat odd number of data points? Let's say they're all between, Q1 and Q4. Let's say none of them lie outside the 1.5 plus or minus Q1 and Q3, but we have odd numbers. And since we're dividing into 4 segments, how would we treat odd numbers of data points?
Right. Well, so I know the answer. Does anyone else have an answer to that? And that's relevant to, I believe, week 2. Hold on for a second. I'm going to stop the share, and I'll show you. Do you have an intuition, by the way, regarding what that is?
To take the average of the data points?
Yeah.
Exactly. So typically, if the median or the quartiles are actually tied to actual data points, we will actually, I'm actually trying to find the relative slide here. But you're exactly right. So the goal here is to look for the average of those values. So let's see if we can find that.
Week 2?
So if we have a median that's like an odd value, we'll take the average of the value just above and the value just below. Since we're on these questions regarding numerical data, what's the mode as a measure of central tendency?
Mode is the value that's repeated most often.
Exactly. So we have the quartile, we have the mean, and we have the mode. I wanted to see if I could find this. Right, we have the mean, median, mode. Let's see if we can find where Ethan describes the median. So median, right, it's the middle number. I like to think of it as the middle number as well.
Mm-hmm.
In most data points, it actually exists. And we give an example in the problem set. I believe in the practice quiz, we have these data sets that are quite small, where you have 5 observations, and we ask which of the following has a median of 8.
Correct. Correct.
I won't give the list.
So this makes sense to me, Nate. But how would we divide 5 data points into 4 segments?
This is where I direct you in terms of answering that question. I believe what you're asking. So if we have n set of observations, so if the n is odd, the median is the middle number. If the n is even, the median is the average of the 2 middle numbers.
So then Q2 is essentially a number that's not existing in the data set. If it is...
Oh, yes, exactly, if it's even. So I'm going to share... so this is relevant to one of the practice questions that I've shown you guys. So we'll go to that. Where in the world can I do a share screen? I'll share. Where's my... Yeah, so let's just say we have a data set. So in the actual... I'm just going to make this as a comment. So in the actual data, we observe... Oh, you know what? I unplugged my keyboard. Hold on for a second. So in the actual question, we have like something like, here's a data set with these points, and what's the median? And then here's another data set where we have what's the median? And the median is the 50th percentile. And all we have to do is, logically, we just rank those values from least to highest value. And then we can say what's the median of this data set, for instance. So here's a data set right here. What's the median of this one? That's the median. It's the median of 4. Because this has 5 observations. 1, 2, 3, 4, 5. Now, if we have 4 observations, what is the median here?
3.
3, exactly. So if we have an even number of observations, we take the average of the 2 middle values. So the average of 4, so we take 2 plus 4 divided by 2. So 2 plus 4 divided by 2. So this is median of even n would be this. There's 4 right there. If we want to print that, we could even say print the median. All right, so, okay. Are there any, I feel like we're focusing quite a bit on the first few weeks in terms of data structures that are related to numerical and categorical data. Are there any other questions related to those first few weeks? Categorical data, numerical data analysis. If not, I want to take us to this concept of relative risk that I think will be very useful, and to revisit these rules of probability, because I think those are key points that I saw a lot of students have issues with. And then move to regression and covariance, or covariance and then regression. Are there any other questions about data? All right. So here I've listed the main probability rules, and I think this is important for us to remember in terms of definitions of probability. So the first couple are just really in the most, so this is all from week 4. And I want to focus the rest of the section on week 4, 5, and 6. And keep in mind, we're not asking you about anything about sampling basics, but I do want us to focus more on probability tables, and then correlation and covariance, and then simple OLS. So I'm going to take us to some actual code. And I'll show this with you later, but I think these are the main rules to think of. First is that the definition of a probability of something is always bound between 0 and 1. And that the sampling space equals 1. In other words, the total probability. The complement rule is 1. So the probability of something not existing is a 1 minus that probability. And then we have this thing called the addition rule. And there are 2 variants of it. And then we have the multiplication rule, and there are 2 variants of that. What's the big assumption of the multiplication rule? If I could quiz any of you on that. I'm going to pull up some of these tallies, because I think this will help us deconstruct some of these probability issues.
Isn't it if they're independent?
Exactly. Who said that?
Suzanne.
Thank you, Suzanne. Yes, exactly. And I actually gave you that little hint here, right? So keep in mind this little pipe here, the probability of B given A, the assumption here is if probability of A given B equals A, or another way of expressing that is if the probability of B given A equals the probability of B. Keep in mind, these are 2 different things, right? If they were not independent, then the probability of A given B is different than the probability of B given A. All right, so it looks like my data set's complaining about running the health data set. And I think I know why, because it's not in the actual on the desktop. So I'll just move that on the desktop. Are there any questions about these probability rules? I'd like us first to work through together just a few illustrations of these probabilities outside of the lecture in a different context other than the, what should I say? Let's see if we can get the data set pulled up for that week. Yep, I'll restart. I know there's a lot of content this week, but I want us to at least understand it fully. Okay. So we should be able to see this. No? Okay. It's because we have this on the desktop. Okay, so here we have this data set, and we did a few of these examples, but I want us to walk through, we'll just do this first one. I'm going to turn this into a table of counts. Require Mosaic. Okay, here we are. This is what I want us to get to. So when we talk about these probabilities, these probability rules, we're going to turn off the margins for now. We're going to set that to false because I want to show you something. So if we want to just convert a table of counts to a table of probabilities, what do we do here? If we don't have access to any of this code or syntax, what do we do? Well, we simply divide it by the number in each category. So, for example, if we look at this number 66, and we can easily see that 66 divided by 560 is 11%. And the percentage is just, you multiply a proportion by 100. So what I want to show is that from these few data, from these 4 categories, these 4 disjoint probabilities, we can illustrate some elements of probability. So for example, if we look at the multiplication rule, or let's just use the first variant of the addition rule. So the probability of A or B is the probability of A plus B minus the probability of both. So what is the probability of, say, the probability of being in fair, well actually, I'm going to round the last syntax to 2 decimal places so you can actually see this. So in this case, what is the probability of being non-poor and in fair health?
12%.
12, exactly, 0.2. And what's the probability of being non-poor or, what's the probability of being fair and non-poor and good and non-poor?
84%.
Exactly. It's simply so here you simply add the probability of being non-poor and fair plus the probability of being good and non-poor minus the probability of both of those. Now, what's the probability of both of those? 0, because these are disjoint probabilities. As a probability table, these are mutually exclusive categories. And this is because, oops, I wanted to print that. So 0.2 plus 0.62 minus 0 is the probability. So it's 0.74 is the probability of being in fair or in good health given that you're non-poor. And the reason we're able to add those and we subtract 0 is that these are mutually exclusive. These are otherwise known as disjoint probabilities, right, as opposed to joint probabilities. Let's see. Now, what about the probability of A and B? Let's say the probability of being poor and non-poor. What's the probability of being in fair health? Fair health and non-poor, fair health and poor.
.2, 20%.
Right. So here we're adding again, right? In this case, it's simply because of the function of the probability, the margins themselves, because these are disjoint probabilities. And we can see that when we look at the margins. If we turn the margins on to true, this also gives us an indication of what the sampling space is. So if you look at the total probability of either of these, the marginal probabilities of health add up to 1, and the marginal probabilities of poverty add up to 1. Right? The poverty are in the columns, and health are in the rows. This entire sampling space is 1, and that corresponds to our second rule of probability. And the rest correspond to our first rule of probability. All right. Now, let's go to this concept of relative risk that we have in the problem set as well. It's relatively simple. What is the relative risk of being in fair health if you're exposed to poverty? Intuitively, if we think about relative risk as the probability of exposure as to not being exposed, and we do this tally function again, right? If we just take from the square, from the basics, then what we have is we can actually express this in terms of two ratios. So this would be the probability of being poor over, right? That's the one relative probability. So this is the probability of being poor, in being in fair health, given that you're poor, right? Because here we have the total marginal probability of poverty, fair health. And then here we have, hold on for a second, okay. I have my columns mixed up. What we want to do here is, let's say, it really depends on our question. I want to do this one more time. I'm sorry. I'm not doing this right. So if we have the relative risk of fair health given exposure to poverty, and we're going to comment that out, then what we want is we want the probability of the event given our exposure, and that probability would be, so this would be the numerator, is equal to the probability of the event of being in fair health given that you're exposed, so that's a conditional probability, which is 0.12 divided by 0.74. In other words, out of all the non-poor, this is why the details matter, I'm sorry. If you look at the proportion, 26% of our sample is exposed to poverty. 8% of the sample is exposed to fair health and poverty. The ratio of people who are both poor and fair is going to be our exposure risk. Right, this is the probability of exposure to poverty. So this is our conditional probability of our fair health given our exposure to poverty. So this is going to be the numerator. No, we don't want that. Okay. Then, as our denominator, we're going to have the probability of the event given that we're not exposed to poverty. And that is simply the probability of being in fair health given that we're not exposed to poverty. And that's simply
0.20.
What's that?
I was going to say 0.20 divided by 0.74.
Right, 0.20 divided by 0.74. And then our relative risk is the ratio of exposure to the total, which is 1.14. And how do we interpret the relative risk here? So it's a ratio of conditional probabilities. And we can say that exposure to poverty increases or decreases fair health. What do we say?
You say something like exposure to poverty is 3 times, or I don't know. I know you say like 3 times or 2 times or 1 times.
Right. So the language I would use is, think about it as exposure to poverty increases fair health 1.3 times, or sorry, 1.14 times compared to those who are not exposed to poverty. And the reason we think of it that way is that's the number you have to multiply to increase your probability or likelihood of being in that risk exposure category.
So in this case, we would say decreases your health?
Actually, we would say increase your health. It would increase your relative risk of being in fair versus good health, because fair here is bad, actually. This was a little tricky in the problem set.
Right, okay.
Fair is actually bad health.
I forgot that.
No, totally understood.
Thank you.
And the key thing to remember is that relative risk 1.00 is equal probability, and we have a written answer, in our problem except for that less than 1.00 is less probability, and then greater than 1.00 is greater relative risk. So here we have a table of probabilities. We actually know the actual percentages. What happens if I say being in poverty doubles your likelihood of a heart attack, of heart disease? What's the limitation of relative risk as a number by itself?
It doesn't necessarily mean causation.
Exactly. Well, it doesn't mean causation. That's a great point. So one is that it's not necessarily causal, right? It's association, not causal. There's another point as well. Here, I'll give you the hint.
I was going to say, it's also general. We can't pinpoint a heart attack. We can just say health in general.
True. Another issue to address is the simple fact that it's also relative. It's not the actual risk exposure. So we can say something doubles your risk, but it may double your risk poverty may double your risk of heart disease from 0.001%, right, to from 1% to 2%. So it doesn't give you an actual size. It doesn't actually give you an actual number. So that's one limitation of the relative risk here. So I think that's all I want to say about relative risk here, except to emphasize that that it can be a little tricky. Obviously, I stumbled through it a little bit in this section. I apologize for that. I want us to move quickly to elements of correlation and covariance, and I'm going to show you I'm going to take us straight to the equations, unless you have other questions about relative risk and probability. Do you have any other questions? Okay. All right. So I'll take us to correlation and covariance. Are there any questions that you have about correlations and covariance in particular that I might be able to help?
This is Suzanne. I had a question.
Sure.
So I understand what the term correlation means, and when I run the formulas, that seems clear to me.
Yep.
I get confused about explaining in English terms the answer that I get when I run either a covariance number or a correlation number. So it's more my frustration with being able to explain in English terms the value that I obtain when I run a formula.
Sure. Okay. And that's crucial when we talk about these kinds of stats. So, Suzanne, just out of curiosity, like if we move from covariance to correlation, I'm trying to think of. Well, I'll take you to this slide. I think like slide 73 is a key slide to remember when we think about correlation and how to interpret it. And this is a key aspect of modern statistics. In fact, correlation is probably one of the most common statistics you'll actually ever run into. It's often referred to as rho or R squared in psychology. So what does it exactly mean? So if Suzanne, if I say there's a correlation of 0.5 between height and, well, let's use a classic example. Let's say height and intelligence, I suppose. That's sort of what Galton did when he looked at regression. Let's say that he said he found a 0.5 correlation between height and intelligence. What would you find difficult in terms of translating that into English?
Well, I would describe it as there's a moderately high correlation between high intelligence and heights.
Right. So I think this is where we have to think about visualization in terms of magnitude of correlation. Correlation is bound by 1 and 0. So what is 1?
very highly correlated.
Exactly. In fact, if you do this, let me clear the screen. I don't know, actually, let's see, eraser. I want to erase everything here. Well, I want to show you this. This is going to be a little janky here, but I just want to emphasize this point. A correlation of 1 means everything lies on a straight line, and it's supposed to be a straight line. In other words, there's perfect prediction, right? A correlation of 0 means what?
It's not at all correlated.
Exactly. There's just a cloud of data points. And somewhere between 0 and 1, we can assess the relative strength of an association. So the way I tend to think of the relationship between correlation and covariance, I kind of think of them as analogous to variance and standard deviation, if that makes sense.
That makes sense.
Yeah. Okay. So if we go to, where is that, 92, well, actually, I'll take us to the first equation here. So on 32. So does everyone get what this covariance of a sample means? The covariance of X and Y. Can you dissect this equation and what it actually refers to? I'll talk a little bit about this. So what we're doing here is we're taking, in our sample, we're taking the average of our X's and we're adding up the product of each X from the average X and each Y from the average Y, adding those up and then dividing it by the number of observations. And then we get this S of X, Y, which is, as Ethan explained, is the cross products of X and Y. So we're trying to just add up all the deviations of the X's and the Y's to see how they relate to one another. Now, why don't we use covariance? Well, actually, I want to ask one question before we continue with covariance. Why do we divide by n minus 1? Why don't we just divide by all the cases for a sample?
Because the mean has a constraint on the covariance.
Right, and this goes back to our question about degrees of freedom. When we estimate covariance, we're actually removing a degree of freedom, the sample average, and then we estimate what is left over. If you can see my visualization, this is what my psychology professor used to do when I was an undergrad. He would say, I'd ask him what are degrees of freedom. He would say, you take one and then you move the rest. So that's the way I remembered it many, many years ago. That's the intuition, and the reason you don't have that for a population is that you know what the sample population mu is, which is in Greek letters. Mm-hmm. Again, that's not a big deal, but just keep in mind that when we talk about degrees of freedom, all we're talking about is what do we have left over after we have the sample. Now, what is the relationship between covariance and correlation? Why don't we use covariance? Right, Ethan clarifies the steps for calculating covariance. Why don't we use covariance? Why do we see correlation so often rather than covariance?
This doesn't give you the strength of the relationship.
What's that?
Covariance does not give you the strength of the relationship.
What does it give you?
It just tells you the whether or not it's the direction of the relationship, if it's positive or if it's negative.
Exactly, Mark, and that's a key point that you'll see time and again. We try to trick you in that. We don't try to trick you, but if you see a big distinction, that's the major difference. That correlation actually gives us, because it's bound by 1 and 0, or 0 and 1, we could say, it's actually in psychology, it's considered a measure of effect size, believe it or not. Even though, keep this in mind, it is actually measured in it's relative to the units that you measure your association. Nevertheless, if I say there's a correlation of 0.6 in one sample and you find a correlation of 0.7 in another sample, we're actually speaking with apples and apples. We're not speaking in apples and oranges. So just keep that in mind, that correlation does give you a measure of relative strength. And this was sort of a, so here's the other statistic to keep in mind. If you look at slide 73, just memorize this and just keep in mind that it's a ratio, again, somewhat like relative risk, right? So you take the sample covariance of X and Y, both, and it's divided by the sample standard deviation of X and the sample standard deviation of Y, that product. So you're seeing how much is the covariance of both X and Y as a function of the variation of X and the variation of Y. So that's how you're standardizing it, essentially. And that's why you're getting it to, and this is like the Greek letter rho that I mentioned earlier. Now, I'm sorry, I said it's bound by 0 and 1. The only reason I said that is I was thinking about positive correlations. I have to underscore, a negative correlation is negative, goes from negative, the actual range of a correlation is from -1 to +1. So what is a correlation of 0 then? What does that mean?
Correlated.
There's no association, in fact. So I apologize for that. I meant to emphasize that it actually is from -1 to +1. The reason we often think about unit in terms of bound by 0 and 1 is simply the fact that if we think about the absolute value of a correlation coefficient, it is between 0 and 1 on the number line. So -1 to 0 is the same distance as 0 and 1. So the way I often interpret or think about correlations is -5 has the same effect size as 0.5, right? -6 has the same effect size as positive 0.6. Right, so, right, Ethan says the absolute value is the strength. So implicit in my previous discussion was I'm talking about the absolute value of R, because that's how we often interpret it in science. Are there any questions about correlation and covariance?
I had one question.
Yes, is that Mark?
Yes, sorry.
Yes, please, Mark.
Can you please distinguish between magnitude and strength?
You like to distinguish between magnitude and strength?
Yeah, can you, I don't know if it's really relevant, but I just was sort of confused. What is the difference between the two? I mean.
That's a wonderful question, actually. And this, I think, is a limitation of correlation in the same way that relative risk is limited. Relative risk gives us a measure of risk exposure, but it's not absolute. In the same way, R, and you'll see that it's bound by 0 and 1 in its absolute value as a measure of strength. I would consider, so think of magnitude and strength as synonymous here, Mark, but not in absolute terms, but rather in relative terms as a measure of association. In the same way, relative risk is a measure of relative association. It doesn't tell us anything about the units or the substantive interpretation. It gives us an idea of the relative interpretation. I would actually, so if you want to sort of mentally pin a slide, I would also consider slide 78 for the week on correlation, because we asked quite a few questions about weak versus strong associations. Strength and magnitude, Mark, I'd say are synonymous here. But magnitude in this context refers to relative strength. It's not an absolute measure. Does that sort of help explain?
Yep.
Okay. Have you guys gone on the discussion board and played that game, that correlation game that I had posted a week or two ago? Guess the correlation? I think it's one of the best examples of, let's see if I can find this, of how to intuitively understand the correlation.
I did have a question about when you were talking about a negative correlation. What does that mean if you have a negative correlation, or do we not ever have?
You have a negative correlation. The only difference is that negative is, so a negative correlation of 0.6, for example, we could interpret as a very strong correlation. in the same way, a positive 6 is also very strong. So correlation gives you both magnitude and direction. Covariance only gives you direction, not magnitude or strength. So positive correlation means a positive association. A negative correlation is a negative association.
I guess I'm trying to get around in my head, like, what does that mean? Like, you know, just in English, like what does that negative correlation mean? Like, I just don't understand.
Okay, let's see if I can show you guys.
I mean, I understand the slope being negative, but what is that telling us?
I'll show you. If I can show you the screen. Can you guys see the screen here of this little guess the correlation game? You guys see this? Guessthecorrelation.com?
Part of it. We're still seeing the slide.
Oh, okay. Share screen, and I'll do the guess the correlation, share screen. Now do you see only the...
Yes.
Good, okay, thank you. So what do you think this correlation is?
Negative.
What's that?
No,
Positive correlation.
It's a positive correlation because we know that as one value increases, the other value increases. But what's the magnitude? I'm pretty good at this. I'm going to guess 0.85. What do you guys think? Okay, so what it shows is that the true R squared is 0.9. So go to guessthecorrelation.com. You'll have to put in your unique identifier. The nice thing about this is it gives you a sort of an idea of what correlation means in real life. So here's another, by the way, in almost all of these examples, you'll see a positive correlation. I don't think they ever give out negative values. But what do you think this value would be? Is it going to be
0.9.
0.9. So last time we had a 0.9, and we saw that it was almost a straight line from 0 all the way up to 1, 1. In fact, here we see more spread. We're actually going to see less. I'm guessing this is more like a 0.45. So the true correlation is a 0.38. I guess 0.45. So if you have any, the reason is that the thing about this is if you know the value of one data point, does it give you that much information about where it lies on the x-axis if you know the value of this data point? Not really. As opposed to this correlation, you even have less information. I'd say this is a 0.3. Okay, so I got a perfect score here, I guess. Or, no, I didn't. It liked what I did. I'm guessing this is a 0.6. Okay, so that's a little bit off, I guess. So that's a good score. So this is a correlation of 0.4. I'm trying to find a good correlation for us. We're going to get... so that was a bit off. This is going to be quite low.
So the point would be if it's a correlation of 1, every point would be on that line.
Exactly. That's what I was trying to say earlier. And I'm trying to... So here we are. That was you, Caroline, right?
Suzanne.
Oh, Suzanne, thank you. So Suzanne, exactly. So look at this correlation right here. I was trying to wait for us to get to a good one. See how everything, all the data points are hugging closer to that line? A perfect correlation of 1 would mean that everything's on a straight line. You have a perfect prediction of your X and your Y outcome. So what would you guess, Suzanne, that correlation right here to be before we had a correlation of 0.4?
You know, higher than that. I don't know whether it would be.
Throw it out.
0.6.
0.6. I'm going to say it's a little bit higher. I would guess 0.8 or 9. So I said 0.8 or 0.9. The true R was 0.8 or 0.9. So just go ahead and play with this. I encourage you. It's a little bit fun, but it also gives you an idea, I think, of in practice. And I'm going to go back to the slides. What these values mean in practice. So that last value, if you notice, Suzanne, I said it was 0.9. That'll give you a good intuition of what an extremely strong correlation looks like, as opposed to some of them which were medium to substantial.
Well, that last one, at least what I was looking at, it looked like there was like a bigger spread, though. That doesn't matter?
there wasn't actually that large of a spread if you think about, let's see if I can annotate on this screen right here. No, I can't. I'm going to draw a little bit. So if you think about this box as a correlation, a perfect correlation has these data points that go straight up the line. The more deviation you have from that line, the weaker the correlation is. And notice we're going straight from correlation in the previous week to what do we have? We have a measure of a simple linear regression. Because all this simple linear regression does is it gives us the line over that, the relationship between x and y. There's a big difference between correlation and the simple linear regression. But for now, just think about, I would say go to guess the correlation, but also keep this measure of relative strength in mind, and keep in mind that correlation measures both strength and direction. Covariance measures only direction. Are there any other questions regarding correlation?
I had one more question.
Sure, go ahead.
Okay, correlation of 0 means, does it mean that there's absolutely no relationship between the two variables, or does it mean that there is no linear relationship between the two variables? That there could possibly some other unseen relationship for our intents?
Although that's a really good question. Well, if it's at absolute, so Mark, this is Mark, correct?
Yeah.
So I'm going to be a little tricky here. I would say a correlation that's really low, like 0.1 or 0.2, we'll say that you could argue that perhaps that's an artifact of nonlinearity. And Ethan mentions that when he talks about the French quartet, if you recall. Let's see, I'm not sure if that's in this correlation here measure, but no, it's not here. Okay, that's fine. But I would say that you could argue that there's no linear relationship, but if it's totally 0, Mark, you really would say that there's no, like if it's 0.00, you would say there's no association between the two. Okay. Sure, Suzanne. Yes. Thank you.
Thank you.
Yeah, and I will save this and we'll record this for later. So the last thing I want to mention is this concept of Chebyshev's rule. So we have the empirical rule. The main point here is that if we have an empirical rule and we have a mound-shaped data set, we could apply it. I just want to tag you on this here, and then also why the empirical rule is cool, because you can basically have the mean standard deviation, and if you know that the data are mound-shaped, then you could talk about the proportions of data within a sample. So just slide 126 and 127. In a way, I'm guiding you towards some of the answers in the practice problem, practice midterm, but I don't want to run you through that. I really would like you to go through the experience of that, but distinguish between that, the empirical rule. So if you know the mean standard deviation mound-shaped, and you know that the data are mound-shaped, if we tell you those 3 pieces of information, apply the empirical rule and look at slide 26 for that. Chebyshev's rule is also relative, but just keep this little factoid in mind, that it's sort of an adjustment of the data. And the main insight here is that 75% of the data fall within 2 standard deviations of the mean. So a question that we might ask is relative to Chebyshev's rule. Those aren't like the central points, but those are questions that we might actually ask as well. Yeah, and Chebyshev's rule is it's sort of an adjustment when the data are not symmetric or mound-shaped. Mound-shaped, you can say 95% of the data lie within 2 standard deviations. Chebyshev's rule is the application of those data to non-symmetric distributions. I don't want to focus too much on that. I think it's more important to emphasize the distinctions between correlation and covariance.
Just a quick question.
Yeah,
would
please.
bimodal not be considered the mound? You would use the Chebyshev's rule on bimodal?
Right. It's not, in a sense, right? Because there are multiple mounds. So you would not say that that's the case. A bimodal distribution or trimodal distribution.
Yeah.
And that's why, in many respects, a lot of these measures of like numerical data, like the measures of skew or even the interquartile plot, they're not always the best measure, right? That's why we talk about histograms and density plots. So if you look at the practice problem midterm, you'll see that I think that question pertains to we display the data using a continuous density plot. And that's precisely because a lot of our measures of numerical data, if you just look at the mean, or if you just apply Chebyshev's rule because you say, well, it's not mound-shaped, okay, we're fine, then you're going to run into problems. So the empirical rule applies to unimodal data, same with Chebyshev's rule. So any data distributions that are more complex, you can't apply those to. Any other questions regarding those issues? Okay, you'll get the answers back from the problem sets, but I wanted to emphasize mostly with the correlation, the distinction between correlation and covariance, and that slide that showed the relative strength of correlations, because not that you have to memorize them, but I think when we were grading the problem sets, in fact, you'll see some corrections that we actually have done. So some of you will get some points back because there's a good argument to be made about whether the answers that we provided were actually fair, in the sense that I think at some point we said there was a relative negative decrease as opposed to a dramatic decrease. Well, it's all really relative to the units that we use. So I'm going to take us to this week on regression, and with the caveat that I know you haven't looked at the problem set responses yet. That being said, most of you have done fairly well on this. Do you have any other questions about correlation, covariance, Chebyshev's rule, the empirical rule, relative risk? Okay.
Actually,
yes, please.
I have a question about any the technical issues that might occur during the midterm. Should I ask you that now or at the end of the section?
Oh, what is not sure. So does that have to do with writing in things and maybe losing work as you go along? Is that your concern?
Yes, I'm worried maybe the internet connection goes off. Then if that happens, who should I contact first?
Sure. So I think this is for everyone. So if you do encounter any of those issues, certainly you should not be a victim of circumstance. Contact the course producer. That's Carrie Foley, if you haven't already, and at least give her a heads up in terms of the fact that that may be an issue for you. I know some people have had that issue with problem sets before, but Natcha, if you have any more particular questions, I'm happy to talk about that with you in terms of your particular circumstances.
Because actually, I'm lucky and I haven't been encountering any internet issues yet, but my internet is not very good, so I might be unlucky and that might happen. So okay. I was wondering if that does happen, and if Carrie is unable to contact me and unable to contact me before the midterm has after 2 hours, then am I able to print it out, fill it in, and then scan it and send it back to you? Would you accept that, or would you say that we don't?
I can't answer that actually. I don't have an answer for you, Natcha, but that's a very good scenario that I think we should definitely address. So I'll talk with the rest of the course staff, and I'll get back to you in terms of what our contingencies are for that, because I know not everyone has perfect internet access. Feel free to email Carrie as well with that particular question. I think that will expedite the answer, because to be frank, I'm not really on that sort of production side, but certainly we don't want to penalize anyone because of their internet access. So email Carrie and CC me, and I'll also independently talk with the course staff to see how they've dealt with that in the past. All right?
Okay. Yes, thank you very much.
No problem. So I want to resume the share. Can you guys see the screen? Let's see. I want to share the slides for simple linear regression. I want us to, if you notice where I had the guess the correlation game If you go to guessthecorrelation.com, you can guess the correlation. You have one variable related to another variable. And I'm just showing you slide 14 from the linear regression lecture that Ethan had. There's some similarity there in the sense that you are looking at the association of one variable with another. What's the difference between correlation and linear regression, however? What's the big difference? Does anyone know? I'll tell you.
Correlation is related to the slope. I would say that correlation and the standard deviation would give you the slope of the line, wouldn't it?
So, yeah, it would give you the slope, but the main point is actually the math behind this and the logic of analysis. So this is what I want to highlight, which is that here the x is always predicting the y. So we have an x variable, and then we have the y, and that's what we measure with uncertainty. So we define our slope in units of x and an intercept, and we define our results in terms of the outcome y, in terms of incremental units of x. So the point is that y has what is called an error term. We measure this with error. But when we think about regression, it's a prediction model as opposed to correlation, which is a simple measure of association. So correlation measures association, and covariance measures association. But regression measures association, presuming that we know x and estimates or predicts y in terms of a 1 unit increase in x. Does that make sense? It's a kind of a fine distinction that I think even a lot of applied scientists don't actually know or really use, but I think that's important to define here. And just think about in terms of the regression line. When we do a correlation, remember I took you to that the correlation equation or the covariance equation. Here we have a different notation. We have that equal sign, right? So we are looking at one variable as a function of the other. That's the main distinction. So they're very similar. They look very similar, but the point is that we're predicting one variable as a function of the other, and that's where the ordering of the variables matters. We could predict, say, the temperature in terms of chirps or the chirps in terms of temperature, and that's where theory comes in. So are there any questions about what the simple linear regression equation means? I'm pointing you to, what is that, slide 18. I think that's the core. So what does the slope tell us? Sorry, what does B not tell us if we have a regression equation?
The y-intercept.
Right, and what is the y-intercept?
When x equals 0?
Exactly. When our x equals 0, what is our value of y? But is it our actual value of y?
Predicted value.
Exactly. It's our y hat. It's what we would estimate y to be if we estimated x to 0. So you set x to 0. 0 times anything is 0. So you just remove that. And here, then we'd estimate the intercept. So that could be an out-of-sample prediction. But that's quite different than a correlation. So I just want to emphasize they're very similar, but they're also quite different. And typically for the exam, we'll give you information on aspects of the linear regression model equation, but we won't give you any, like, we won't demand of you to actually use any R coefficients or anything like that, or estimate R. But you might have to estimate, for example, the intercept, the predicted value of y given, say, a particular value of x, for instance. And that's where you just simply define the equation. You write out the equation here in terms of the intercept here, and the slope. So B1 is equal to what in this example?
0.2307.
Exactly. And what does that tell us? If we increase the number of chirps by 1 unit. What's that? I'm sorry? Okay, I thought someone might have had another question. Okay. So it tells us what our y increases by if we increase our unit x, or x by 1 unit. So if you increase by 1 chirp, you actually increase the temperature in Fahrenheit by 0.23. Your predicted value, rather. The actual value is not predicted. All right, I want to go to some of these concepts that were issues when we did the problem sets beyond interpretation. What is this concept of a residual?
The difference of the predictive value as opposed to the actual value.
Right, exactly. So the residuals is that which we don't really define in our regression model. So sometimes, like when you do sort of guess the correlation analysis, as I showed you, if we try to fit a line that predicts our outcome, sometimes we're not very good at predicting that outcome. And in that case, we'll have residuals that are quite large. Now, if we look at the sum of squared errors, this was a concept that I think a lot of people had issues as well. What does this mean, and why does a regression model assume that these are as small as possible? This was actually a question. I think we misworded that question. I hope it wasn't misworded in the practice midterm. But what does this mean to minimize the sum of squared errors? What is the ordinary least? Why would we call this OLS, or ordinary least squares regression? Well, the way I think about it is that SSE is simply that method of fitting the regression line in a scatter plot of points where we try to minimize the distances between those points. So the regression will struggle, even if the data don't really fit that well. So for example, Mark, you asked what happens if there's a correlation of 0. If there's no association, you'll probably see a linear regression line of x predicting y being horizontal, actually, which means that no matter what the value of x is, it doesn't change our interpretation of what our value of y would be. But the sum of squared errors is simply the fact that it's a consequence of the brute fact that we can't add negative values and positive values. But we want to look at the distances of the observations from the data. It's a measure of disparity from our model and the data. And we want to minimize those as much as possible. Someone had asked about last week about whether they have to know calculus or anything like that. And I'd say no, intuitively you don't have to know anything more than the fact that when you fit a line to a plot of data, you're simply trying to minimize those distances, minimize those residuals. So yeah, Ethan points out that each line has a different SSE, but we're looking at the overall sample SSE, sum of squared errors. And so, for example, for this data set, you just simply try to fit the line the best you can, and that's simply you're trying to minimize these distances right here. Make these distances the sum of these distances as small as possible. And that's what the regression line comes up with. So you always have one regression line for every scatter plot of data. There aren't multiple regression lines. There's actually just one. And that's where calculus comes in, but you don't have to know, about calculus when interpreting that. Most of the other questions I think from, let's see, hold on, I'm trying to get out of the drawing. Yeah, most of the other questions that I saw in terms of the regression lines, yeah, so Ethan talks about calculus, but most of the other questions I saw spoke to the relative size of regressions, and I want to show you, I think this is where, again, an intuitive approach helps. If you want to understand least squares regression, hold on for a second. Have you guys been to this demonstration before? This is another demonstration that I think shows the analogous association. So here we have guessed the correlation. Now we're going to go to Wolfram Alpha, and I'll share the screen here. Wait. Hold on, sorry. Okay. Let me share the screen one more time. Okay, good. So if we interact now, no, she doesn't want, I think it's asking me to download something. Sorry about that. See if we can interact here. So if you can show the least, well, apparently I'm having trouble doing that. The point you want to make here is if you're squaring these values, you're actually making it so you can add them up. You can add up a positive value and you can add up a negative value. And that's what we had, I think, with question 20 of the last problem set. If you add up just the residuals, they add up to 0. But what we want to do is we want to actually have a non-positive sum of squares, so that way we can develop our estimate statistics that give us a relative measure of variance. And this is where we go to this, what R squared is. Now, what is R squared? Can you guys hear me? So this goes to decomposing variation.
Yes, we can hear you.
Oh, okay, thank you. Okay, so R squared is interesting because it's essentially a measure of fits.
The screen is black, though.
Oh, really?
Blank.
Okay, thank you. I didn't mean to do that. Okay. So this is where I take us to part 3 of the lecture, where we talk about what R squared is. R squared is the variation in the y that is explained by our regression model. So, and that's the coefficient of determination. What is 1 minus R squared? It's actually that which is not explained by our regression model. So let me see if I can show you what R squared is. Yeah, so here's our R squared. So you might, it's just relative to, I mean, relatively important to understand, in the sense that if we think about what a correlation is, we can also think about R squared as a sort of analogous to a correlation, although it's quite different because of the way that we estimate it. So correlation is the model sum of squares, that which we explain by the model. It's a ratio of that which we explain to the total sum of squares. So all of those squares that we add up in the data set relative to the regression line. So it's that which is explained versus the total amount of variation. And the reason we are interested in R squared is that it tells us how predictive our X is relative to our Y. And the opposite of that is our sum of squared errors, which is, again, these are the deviations from our regression line. So those little boxes that we see, those unexplained residuals, all added up as a function or as a ratio of all of the sum of squares. And here we see something analogous to the correlation coefficient, the R squared, to think of it as the relative explained variation in the outcome. Are there any questions about sum of squares? I know some of this can get a little complex. Most of what we ask for in the midterm are some simple plug and chug, answers, like what is, or interpretation, issues of interpretation. Can you interpret a regression line? Can you, if I give you the intercept and the slope, can you define those values? Can you define what a residual is? Can you define what R squared is? Are there any questions about simple linear regression that you have questions about?
Right here, when you have the SSE, that's the residuals, correct?
Mm-hmm.
So what is, explain again the MSS, is that?
So the R squared is a model sum of squares. So if we look at, if we just go to the previous slide, this is slide 114 of week 6. So what we have here are the sum of squared errors. See how that's in red? These are
Right.
all of those residuals that are not explained by the model. And the MMS is simply those that are explained in terms of the model. Or sorry, in terms of the mean, sorry.
Okay, so it's from the mean.
I'm sorry, model sum of squares. We're talking about regression models, right? So here we have the total sum of squares, all these deviations. We have the model sum of squares, which is the variance of y, and then minus what we have. And then the residual, or the sum of squared errors. These is what we cannot explain. So think of the total as a product of that which we can explain and that which we do not explain in our model. So these are the sum of squared errors that we explain. These are unexplained. And this is the total. So when we talk about R squared, we're just taking the ratio of this divided by this. What do we explain versus what is the total variation in the outcome? When we talk about 1 minus R squared, we're just taking the residuals, 1 minus the residuals and as a function of the total sum of squares.
When you go back to the previous slide, that dotted line going across is the mean. Is that correct? The black dotted line?
This one right here?
Yes. Yeah, that one right there.
So this is y hat. This is the mean of y.
Or is that, okay.
So this is
Okay,
the mean of y as opposed to y hat, which varies for each value of in our data set. So for each person I, so whenever we talk about regression, we're indexing our observations by the ith observation is what we'll call it. So y-ith means that for person, let's say we use the Titanic data set, for the person in the Titanic data set, we estimate that individual regression, the person's sum of squares errors as that value, that person's value minus the average value for the sample. We square it and we average that up for the entire sample for all observations within the data set. And that's the total sum of squares. That's the total variation in the data unexplained by the model, as opposed to those sum of squared errors that are explained by the model, right? And you can see that here intuitively, because here you have the model sum of squares, the error sum of squares, which are equal to the total sum of squares, right?
Okay, so let me make sure I understand it. This MSS is the unexplained.
The MMS is the explained. So think about it this way. R squared is a measure of how much we explain in our outcome y. Therefore, it is by definition
Okay, I got it.
that which we explain in our data set,
Okay.
as opposed to everything. So R squared is actually, let's see if we can annotate this. Right, so R squared, is the ratio of what we explain over everything. Right, this is explained. And then that's the main insight here is what can we explain by our model and what's the ratio of what we explain to the total variation in the outcome.
Okay.
And so the higher the R squared, the higher the variance explained in our data set. I hope that's intuitive enough for you. I know it's not perhaps the easiest explanation, but let me do a new share. So what you asked about before, keep in mind R squared is what we measure, is a ratio of what we measure to the total variation in the outcome y. That's just the intuition. Just think about what varies, what do we explain and what is unexplained, or what is the total variation and what proportion is that. Now 1 minus R squared is that which is unexplained by our data set. So we can also say what we explain in our data set, I'm going to say this in a weird way, but our R squared is also 1 minus the unexplained variation. This is unexplained. So if we do the inverse of our unexplained, if we do the total minus this, then we're left with this as a function of this. But I know this is a little confusing, but the main intuition is what do we explain in our data versus what do we fail to explain? And the reason we use sum of squared errors is so we can add up the residuals. Now this concept of the root mean RMSE, the square root of the mean squared error, is the last concept I want us to bring us up to. It's analogous to R squared in the sense that we're still trying to explain the outcome in terms of our model, but it's simply, again, what we're doing, the intuition here is relatively the same. We're taking our squares and then we're dividing it by the number of observations effectively. Here we have n minus 2 because we use up 2 degrees of freedom, our intercept and our slope. All we're saying is we take our variation in the outcome that we try to explain, and then we divide it by the number of observations, and then we give an average value of how much on average our data are unexplained. So I think Ethan's example here is quite useful in terms of comparing R squared as a measure of model fit as opposed to RMSE. So for Galton's data, the R squared is 0.1. Fairly small, but it means that 10% of the variation in heights among children is accounted for by heights in their parents. In other words, whenever you have an R squared of 0.1, you're saying 10% of the variation in Y is explained by the variation in X. And so then for R squared, you could have any number of RMSE. But here we're talking about units of the outcome in our model, right? Because RMSE is in terms of units of Y. So here we're talking about inches and height. So it tells us on average how off we are in our prediction model. So our two main measures, R squared is more common, RMSE is simply how on average are we off in terms of our measure, in terms of our outcome measure. So are there any questions about these issues? Here you can see, I think in the other example, Ethan gives a poor model fit, but he also explains how RMSE is also explained in units of Y. I think these if you just sort of try to bypass maybe the complexities of some of these equations and think of the intuition that we're just trying to predict Y given X, and that we have two measures of fits, and that we're fitting it using a simple intercept plus slope equation, I think that's the best way to go ahead with this and try to wrap your mind around this. Any other questions before we go? I think it's time to wrap up, but if not, I think we'll end. Any final questions? Okay, I'm going to summarize with this. First, in terms of preparation, take the practice midterm if you haven't already. Second of all, put on your discussion board any questions that you might have when you answer those questions. Third of all, do it earlier rather than later. You'll have until the end of Wednesday to actually work on the problem set. And I'm here, the rest of the staff is here to help you with any answers, any questions that you might have. It's our goal to help you. We want you to learn these concepts. And I know that not everything can be covered in half of a course within an hour and a half, but I tried to sort of point you in directions that I think reflect perhaps the difficulties we've encountered so far. So I hope this has been helpful. All right. Thank you very much.
Thank you.
And Natcha, if you want to stay on in terms and address some technical issues, feel free to do that, okay? Thanks, guys.
Thank you so much. I actually have to leave now because it's